Now that we have understood the physical properties, we will now understand conformations in case of alkanes. Alright, so conformations is a kind of isomerism. I can say that. Before I get into the topic, maybe we should briefly discuss the kinds of isomerism that we have studied, uh, especially in alkanes. Okay, forget about alkanes in general. Isomerism, we have studied structural and stereo. Okay, there are two kinds. And in structural, there is chain if the parent chain itself is different, and then you have a position if the position of the functional group is different. Functional, the functional group itself is different, and metamerism. Okay, that is the number of alkyl groups on either side of the functional group. Okay, so we have studied all of that. And then when it comes to stereoisomerism, I told it is there is no change in the structure, there is only change in the geometry. Okay, and this is very much similar to that, but we still do not call it a stereo because it is not complete isomerism. Okay, it is just that something is rotating, the position as such is not changing. Okay, so if in alkenes we will be doing the complete stereo isomerism, geometrical isomerism. Okay, we have geometrical and optical. Optical isomerism in case of stereo you will be studying in class 12. This year structurally you have already studied all the four in the first chapter. Stereo, an example of that one subset of stereo, that is geometrical, you'll be studying in alkenes, which will be in the next video. But this video is conformations. The reason why we do not place it under isomerism is because there is no change in the position as such. Like maybe if you try to refer the geometrical isomerism after this video, you will, and then come back, maybe you will be able to relate that point. But for now, just focus that it is a kind of isomerism, yet it is not in reality an isomerism. Okay, so like I said, it will be more clear when you actually understand the meaning of geometric isomerism. Okay, but this is definitely not something wherein there is structural changes. Okay, so this is the background. Now let us get into the topic. So conformations, you know, alkanes, everything is a single bond. The carbon-carbon sigma bond, you know, it is single bond, so everything is a sigma bond. And you know the shape or the symmetry of this. It is symmetrical, tetrahedral shape, most of them, right? So you have studied this sp3 hybridized. Symmetrical around the internuclear axis. What is the meaning of internuclear axis? This is the two nucleus. If you have two carbon molecule, that is ethane, this bond is symmetrical. Okay, it is symmetrical about the two internuclear axis, and because of this it allows free rotation. Because it is symmetrical, there is possibility for free rotation. It allows for free rotation. Okay, and because of it results in the formation of different spatial arrangements. Now what is the meaning of this? I'll tell you. Okay, so the carbon-carbon sigma bond is very symmetrical in case of alkenes, and the symmetrical about the internuclear axis, and this allows free rotation, and because of that it results in the formation of different spatial arrangements that can change gradually. Okay, and when this arrangement happens, it results in the twisting of the CC bond. This spatial arrangements, what you see, is because of twisting of the CC bond, and that is what we call as conformations. Okay, so I'll just show you this. I have a few, I'm just trying to arrange this so that you understand. I'm taking the example of ethane here. Alright, so yes, let me just give me a moment. I'll just try to hold it in two hands probably. So difficult for me to hold slightly, yes. So this is how an ethane molecule C2H6 roughly looks like. Okay, you know it's tetrahedral. Yes. Just a second. I'm dropping one pen every time I hold it. Okay, let me try to hold it tightly. Yes, I think yes, this is how it is. Okay, so if I hold it like this, imagine between my two fists are like carbon carbon atoms here in case of ethane. Alright, so two fists are carbon atoms and there is a bond between. I should have showed you up with a pen, but I cannot hold that pen. Alright, and if there is a bond, because it is symmetrical, the bond which is between my two fists, that results in a slight twisting like this. So, and when the molecules twist like this, they kind of rotate like this. Okay, because it is symmetrical, it allows for free rotation. There is only one bond. It is like, imagine you have one thread between two points and that thread is allowed to rotate. So what happens? What is there at the end of these pens? End of these pens you have an hydrogen, correct? This is carbon, three hydrogens here, three hydrogens here. That's how it is C2H6, correct? So when I say this internuclear axis, this is the axis between two of my fists, which is two carbon molecules. All right. So this internuclear axis, about that axis, the carbon-carbon sigma bond, you have a sigma bond, it can rotate slightly like this. Okay, it can twist like this, and if imagine there is a bond in between, and if it's able to twist, what happens? The whole molecules get slightly rotated, and that is resulting in conformations. All right. Now there are there is a term which is called as torsional strain. I'll come to that. Okay, so what I want you to highlight is, you now can understand that there are various positions, right? See, there are infinite conformations. See, if this slightly rotates, I don't know if you can make out, maybe like this. If I see, hold it like this, it is like exactly symmetrical, right? They are like parallel to each other. And then if it slightly rotates, one comes like this, correct? So if it slightly rotates, maybe this is one conformation, this is one more, this is one more, this is one more. I have infinite number of conformations depending on how the bond between the carbon-carbon rotates, by what angle it rotates, that decides the amount of conformation. And in reality, I have infinite conformations, but we are only dealing with the two kind of conformations, that is eclipse and stagger. Okay, so we are taking the two extreme cases here. So eclipse is like this, exactly what I have shown is eclipse. Okay, where all the hydrogen are parallel to each other. These two are parallel, these two are parallel, and whatever you see down, these two, the black and the blue down, that those are also parallel. This kind of position, I'll draw it and show you. Okay, but I was able to hold it with great difficulty, so I thought first I should explain this. Alright, so this kind of position where the hydrogens are parallel to each other, the bonds are parallel, and at the end of the bond there are hydrogens. Okay, so each set is parallel to each other. That is what we call as the eclipsed transformation, eclipse conformation. Alright, not transformation, conformation. What is eclipse conformation? One possibility wherein the bonds are exactly parallel to each other. All the bonds are parallel to each other. Okay, I'm just showing it to you in all dimensions. Now, what is so special about this? What do you think about it in terms of stability, in terms of repulsion? Alright, so you can just look at that you know, the carbon on the top of this, there is a carbon, hydrogen. There is a hydrogen here, there is a hydrogen here, there is a hydrogen here, there is a hydrogen here. All the tips of the pen have an hydrogen. Now, in this position, the distance between the hydrogen is minimum. Do you see that? If I rotate it slightly, you know, this distance is becoming greater, correct? When they are parallel, minimal distance. If I rotate it, the distance is going to be greater. So, when I have the eclipse conformation, that is, when the bonds are exactly parallel to each other like this, then it means that the distance between the electron is the closest, distance between the hydrogen is the closest. And if the distance between the hydrogen is closest, what is bond? Pair of electrons. So there is maximum repulsion. And whenever there is a maximum repulsion, maximum energy is involved to make, you know, to repel them. There is maximum energy which is associated. So minimum stability. Alright, so it has got minimum stability. So eclipse conformation has got minimum stability. There is also one term associated which is called as torsional strain. What is this torsional strain? I told you the carbon-carbon sigma bond, because it is symmetrical, it can kind of twist about itself. But it is not completely free to twist. there is a kind of strain on that molecule because of the weak repulsive forces between the adjacent bonds. They will kind of repel the twist. They will try to kind of oppose it. And that strain, or in the form of interaction between two adjacent bonds, it can be any adjacent bonds, that is what we call as the torsional strain. You can visualize it like a kind of resistance to the motion. Alright, so this motion, what I'm saying, the twisting of the molecule, which is giving me different conformations, it is not that free as it appears. There is a kind of strain which is opposing it, and the strain is because of the repulsion between the bonds, because here also I have electrons, here also I have electrons. If I try to rotate it, these electrons, they try to resist that change. Okay, so that that strain, which is basically due to repulsion between the electron cloud, that is what we call as torsional strain. And um, in case of ethane, it will take about 20 kilojoules per mole of energy. Okay, 20 kilojoules of mole is what it takes when I try to rotate it. Okay, now this is just a term, I don't think they'll ask you. Most of the important thing is what is eclipse and what is the next one. Okay, now I believe I'll repeat eclipse before I go to the next maximum conformation possible. So eclipse, what is this conformation? The eclipse conformation is that structure wherein the opposite bonds, or the bonds, are parallel to each other. This is parallel to this, these two are parallel, the bottom ones are parallel. And this is the position where the distance between the electrons, I should say hydrogen, but here it is a bonded pair, so I have electrons here, correct? So distance between the electron is minimum. If the distance is minimum, obviously repulsion will be maximum, that means more energy, lesser is the stability, max is the strain. The strain is more because there is more repulsion. More the repulsion, it is trying to resist it, like a tension you can visualize. Maximum is the strain. Alright. Now, what is the other possibility? Other possibility is that you slightly rotate it. The max one is like, when it is exactly like this. If you see it in the front view, it is going to be like this. Okay, I don't know if you can see it. Yes, this I think it's like this. Yes. Okay, where, they are exactly, this was like parallel. If it rotates and if it exactly comes here, just focus on this 3 pins on the top. Okay, ignore the black pins. So this is like exactly one bond is, instead of being parallel, it has now rotated and obtained a perpendicular position, perpendicular to this molecule. So this pen, focus on this pen and this pen. Okay, they were or maybe this black pen. Okay, so these two pens which were parallel. Now if I rotate it like this, this is the maximum position, because if I go further, it's again going to be parallel because this is going to come first, right? So it's something like that. So that's the reason. The next position, maximum position, is when they are perpendicular to each other, and that is what I call as the staggered conformation. And in staggered, now if you just focus on the tips of these two pens, okay, you can understand that when they were parallel, there were minimum, only focus on these two pens. When they were parallel, distance was minimum, so repulsion was maximum. But I move it like this, of course the distance will be more, correct? I hope you are getting that. Okay, so in case of staggered conformation, it's exactly behaving the opposite of what was happening in the case of eclipsed conformation. So staggered, I'll try to show it to you correctly. Just give me a second. Yes. Okay. Yes. So in case of, this was eclipse, correct? So in case of staggered, something like this is happening. This is coming in between. Okay. So this should also come in between, but I'm not moving it with the correct angle. Yeah, I think this is how it is. Correct. So everything is coming in between. So there is perpendicular thing, and because it's perpendicular, if it was in one plane, it was closer. Now it is shifted like this. Obviously, the distance is greater. Correct. So in this case, what do you see? The distance is far, but repulsion is minimum. That's why minimum energy, more is the stability. Okay, now let us try to understand with the help of a diagram. So before that, I will write torsional strain here. Torsional strain is torsional. What is this torsional strain? Torsional strain is basically a weak repulsive interaction, weak repulsive interaction between the adjacent bonds. Okay, and it uses about 1 to 20 kilojoules of energy per mole. Alright, so that energy which is required to overcome the torsional strain. Torsional strain is like a kind of tension you can figure out. It's a kind of resistance. It tries to resist that change. The more you want, the more is the repulsion, more is going to be the strain. Alright, so torsional strain is a weak repulsive interaction between adjacent bonds, and it has to overcome an energy barrier of 1 to 20 kilojoules per mole. And you have two kinds of conformations at the maximum conditions. In general, there are infinite, but we are only going to do the two kinds. One is the eclipse. I will write it as a difference so that you can understand this. One is eclipsed conformation, and the other one is the staggered conformation. Eclipsed is when it is, let me write the diagram also as it is in your textbook. So it is something like this. Okay, it's not in a plane, it's in a 3D. I hope you're getting this. Let us say that there's a bond here. This is parallel to this, this is parallel to this, this is parallel to this. So parallel, 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 parallel. That is eclipse. So it is, the bonds are parallel here. Okay, and then let us write it. So the electrons, that is, I will just write it as hydrogen so that you understand. Electrons are closest. Okay, it is exactly like my finger. Electrons are closest, but if I rotate it like this, it's going to be increasing the distance. Exactly like that. Because they are closest, maximum repulsion, and if there is maximum repulsion, you need maximum energy, more energy. Alright, and more the energy, minimum is the stability. It all relates. See, you just have to remember eclipse as this. Bonds are parallel. If you know this, easily you can write this. The moment you say bonds are parallel, electrons are closest. They will repel the maximum. Then more repulsion, I can even write more is the torsional strain, because more repulsion, what is torsional strain? Repulsive force, right? So more repulsion, more strain, maximum energy, minimum stability. Okay, and how do I draw it here? Because they might ask you to draw it. It will be something like this. Let me draw the first carbon as it is. For the second one, this bond is now here. Do you agree? So this bond has rotated like this, whereas this bond would have rotated like downwards. This has come down and this has moved like this. Okay, so it's perpendicular. I showed you that. Let me once again show you so that it's clear. In the case of staggered conformation, yes, let me try doing this. It's a little difficult for me to hold it. Okay, yes, I think yes, I'm almost there. Okay, so this was eclipse. Remember, parallel, 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 parallel. Staggered is like this. Exactly this comes in between this. Okay, now everything should come between, literally. Yeah, something like this. This is staggered, and you see that the electrons are at the farthest distance possible, whatever is possible in the given structure. That is why everything is opposite, right? The bonds are perpendicular. You can say that. All right. So electrons are at the farthest possible distance, and because of that there is minimum repulsion. And if there is a minimal repulsion, there is minimum torsional strain, because torsional strain itself is the repulsive interaction between the clouds, electron clouds, right? So more the repulsion, more is the strain. So they can ask you questions like in which conformation it is more and all that. And then minimum repulsion, so minimum energy required, and minimum energy, maximum stability. Okay, and anything in between them, this is parallel, this is 90, correct? Anything in between them, okay, that is what we call as skew conformations, and you have infinite number of skew conformations. Alright, now also we will understand how do I know this is a 3D structure. I had to do a lot of circles to explain you, and I hope you have understood it. Alright, but if I have to draw it in 2D, how do I project a 3D view on a 2D? Let us try to understand that now. Okay, so yes, there are two ways to represent it. One is what we call as the seahorse projection, and the second one is called a Newman projection. Both of them are important. Okay, so what is the seahorse? When you are viewing the molecule along the molecular axis, okay, the angle how you view it is along the molecular axis, and you see something like this. Okay, I'm not drawing the carbon here, so the angle is 120 here. So if one of the carbon is like this, the other carbon will be parallel, parallel, parallel. So this is something like this, and this is the molecular axis. Okay, and this is for eclipse. Okay, for staggered, how will it look? Let us say you have the same thing here down. Okay, for staggered, if you view it, how will it look? This would have shifted like this. It's in between now, so somewhere like this. This would have shifted here down, and this would have shifted like this. So each bond has come in the center. This has come here, this has come here, this has come here. Okay, so this is your staggered conformation. Alright, now Newman is when you are viewing from the CC head-on side. Okay, it is like, you're trying to view it from, let us say that two molecules are like this. I have held it like this. What if you're viewing it from this angle, CC head-on? Okay, so this was 2 carbon, and I had like, so many pens coming out. Maybe I should have just shown you with the help of my fingers. Yes, this was much simpler, I guess. Yes, anyways. So if I view it like this, CC head-on, what do I see? In case of eclipse, I see something like this. Correct? It is almost on top of each other, parallel. I cannot see things, right? It's like, if I see like this, okay, head-on side, now these two are parallel. Think about it, these two are parallel. If I see like this, what do you see? Everything on top of each other. I hope you're able to visualize that. And in case of staggered, you will see something like this. Right? Like something like this, because everything is in between. Something like this. Right? So this is for staggered conformation. Okay, so that is it about conformations. Visualize this. The representation is important. They might ask you to draw, or they might give you a figure asking you to answer what kind of representation it is. Or even eclipse and staggered are the basic ones. Where is it? Minimum repulsion, maximum repulsion. I'll summarize. Eclipse is when they are parallel, and the idea of conformation is that when you have a CC sigma bond, there is always a scope, because it is symmetrical. It can rotate about its internuclear axis, and when they rotate, it results in the twisting of the bonds and by certain angles, and that is what we call as conformations. In general, there are infinite conformations possible, but we study the extreme ends, that is eclipse, when they are parallel and electron repulsion is minimum. So closest maximum repulsion, distance is closest, maximum repulsion, maximum energy, minimum stability, maximum strain. What is this torsional strain? It is the weak repulsive force between the interaction of two bonds, okay, or between two adjacent bonds. So kind of resistance I told you. And in the case of staggered one, it is the maximum possible. It will come something like this. Correct? If I just show you in this, it is something like this, where this parallel one has shifted like this, or it has exactly come in between the other two bonds. Right? That's the maximum possible. And in that case, there is a maximum distance, or minimum repulsion, minimum energy, maximum stability, minimum torsional strain. Yes, I'll stop this for now.